Alright, so quick review of distance versus displacement. It's going to be a big part of some of our problems. We briefly discussed it early on, so just a few more specifics with some helpful vector diagrams. Alright, first of all, remembering what a scalar and a vector quantity is. A scalar is something without direction, doesn't care about it, doesn't include it on its answer, and a vector does consider direction and would like to stress it on its answer. So the situation I have is, let's take a person walking with two segments of motion, or running, whatever, maybe from a rabid rat squirrel like on your last test, whatever you could imagine. So we've got a motion starting from a defined origin right here of 10 meters. Let's say the person stops for a moment and then goes 5 more meters in the same direction, which we'll call east this way, west this way. Now, if I asked you for distance, distance is a scalar quantity. It does not care whatsoever about any factors with direction. So we usually just represent plain old distance d. At least that's the way I'm going to do it. And if we wanted the total distance and nothing else for the first scenario above, the man went 15 meters. And if we want displacement, how we usually represent displacement is a little more specific. Delta change in x. And what that really tells me as a symbol is from where I started to where I ended. Now remember, this one is a scalar right here. Let's write that beside it. This one is a scalar quantity. Delta x is a vector quantity. Well, since delta x is a vector, that means we should be able to also illustrate it as an arrow on our diagram we will in a second. Now, where I started to where I ended happens to be also a magnitude of 15 meters. We're going to stress east though, since this is a vector. So what we could see here is that we've got the same magnitude, but that doesn't always happen, and we'll see why. But let's first go to making a resultant vector representing displacement, resultant displacement. We can't draw a vector representing distance because we can't draw a vector arrow because it doesn't have direction, so it wouldn't make sense to represent it as an arrow. But so this red line is going to represent this displacement from where I started, boom, to where I ended. We'll draw it below it, even though we could imagine it over top because we're on a one-dimensional x-axis number line kind of deal here. Alright, now let's see how that could change down here at the bottom. We're going to take the same person doing almost the same thing. He's going to start off going 10 meters east. He's going to stop, but this time he's going to turn around and backtrack. Again, that should technically be drawn over top of this one, but we usually don't do that for sake of it getting messy. So we'll just start a new line below it, but that just means he doubled back along the same axis. So let's answer the same questions we did a moment ago. The scalar quantity first. How far did this guy go? Regardless of directional change, the answer is still 15 meters. The distance does not, since it's a scalar, does not care about him turning around. It's just how far did I go? That's it. Now is where we get a big difference, and that's when I ask for displacement. Or in other words, again, displacement means where I started to where I ended. And this time first I'm going to draw in the vector arrow that represents that. And where I started was here, but this time where I ended was here. So there's a graphical representation of my displacement, or in other words, delta x. And we could see that that answer, that arrow, does not represent an arrow this long of 15 meters like it had in the previous situation. So what we have here is some really basic math. Obviously 10 this way, 5 back this way means this leftover piece from beginning to where I ended has to be 5 as well. We also want to note that it's still pointing east, so 5 meters east is our correct answer for our displacement. So I just want to stress one more time that when you have a time interval of something happening, if there is no directional change, the magnitude or size of the distance and displacement are the same, but when they're in that given amount of time is a directional change, and we're looking at that whole trip as a whole, then there is going to be a different magnitude for the distance and the displacement. And we're going to carry this along into the next example of velocity and speed. We'll have to remember the same scenario.